Hello everyone, welcome to Hdfs Optimization, Stabilization, and Supportability. My name is Chris Naroth. I'm an Apache Hadoop committer and PMC member. I work at Hortonworks as a software engineer, primarily working on Hdfs. And before I joined Hortonworks, I was a user of Hadoop, operating, deploying, maintaining clusters. And so as a result of that, I have a tendency to want to do what I can to improve operations life for Hadoop.
Hi everyone, my name is Arpit and I'm a Hdfs developer at Hortonworks. I'm also an Apache committer and a PMC member on the Hadoop project.
To motivate today's talk, I'd first like to bring up a couple of high-level points that we've observed in our time running the system. We find that very often Hdfs engineers are on the front line for operational support of Hadoop. And I think this is very natural when you think about the fact that Hdfs is the foundational storage layer for the Hadoop ecosystem. Alternative file systems are also supported. We have support for integrating with various cloud storage providers, for example. But certainly, by and large, the common case we see is Hdfs deployments. And therefore, challenges in Hdfs have the potential to impact the entire Hadoop ecosystem. And then conversely, application problems very often manifest first as problems that are visible at the Hdfs layer. So for example, if an application is running inefficiently and generating high load on the system, that can often manifest as overloading Hdfs. In the past, we've done various analyses on support cases, and we've observed some trends. And we always come back around to thinking that anything we can do to improve stability of Hdfs is certainly going to improve stability of the ecosystem as a whole. So it's a good area for investment. And looking specifically at those challenges informs what we need to do in the software to improve it. And a couple of themes emerged from looking at that. What were the potential software improvements? I'd say those themes are optimization, identify and mitigate bottlenecks, stabilization, prevent unusual circumstances from harming cluster uptime, and supportability. When something does go wrong, provide visibility and tools to help fix it. Today we're going to be presenting a series of Apache Jira IDs talking about changes that have been made. I want to make it clear that we're very thankful to the entire Apache community for these contributions. Even though we're presenting this, it doesn't represent just our work or just the work of our Hdfs teammates. It's really the whole community. So thank you for that. And if any of you in the audience are the author of a patch that we're about to reference, thank you very much. First, I'd like to talk about a topic of performance. And in this area, garbage collection is something that comes up a lot. It's well known that the name node, as the central point of metadata for Hdfs, as the file system grows, its requirement for a JVM heap that can support all of that metadata grows. And as JVM heap sizes grow, it becomes more critical to configure garbage collection well so that a long stop-the-world garbage collection pause won't cause trouble for the system. Another interesting trend that we've seen recently is that data node heap sizes are increasing as well. And this looks to be an effect of hardware trends. Some people are choosing to run with a smaller number of denser data nodes, so more volumes attached to the node or larger individual volumes. And because of that, that increases the memory footprint required for an individual data node to track block state. And there's been a lot of information written about garbage collection tuning for large JVM heap processes. In addition to it, we have a set of recommended best practices for configuration around that. But in addition to that, what are some things that we can do in the software to reduce garbage collection pressure? And one particular area for that is block reporting, which is the process by which data nodes report information about their stored blocks to the name node. This comes in two different flavors. One is the full block report, which is a complete catalog of all the blocks that are stored on that data node. This is something that is pretty costly to do and sent only infrequently. The other flavor is the incremental block report, which can be sent much more frequently because it's communicating small delta state, just individual additions and deletions of blocks. All block reporting is something that occurs asynchronous of any user-facing operations, so it doesn't impact end-user latency directly in most cases. However, we have seen that inefficiencies in block reporting can overwhelm a cluster to the point that it does start to impact end-user operations. One enhancement in this area is Hdfs 7435. This issue looked at the way we were encoding in memory the block report data structure. And Hdfs RPC, like a lot of RPC in the Hadoop world, uses Google's protocol buffers for encoding messages. Those block reports were declared to be encoded as a sequence of 3 64-bit long fields for each block. What was not clear from this was that behind the scenes, if you dug into what protocol buffers was doing, this would translate into an array list of integer objects with a default capacity of 10. And for just about any data node, that was not going to be large enough. So once more blocks would be added to that, it was almost guaranteed that you would need to reallocate that array and grow it multiple times to accommodate the full list of blocks. So this would be a source of reallocation churn and garbage collection churn. Added to that, since these were the capital I reference type integer, there were the attendant boxing and unboxing inefficiencies that come along with that as well. The solution to this was a more garbage collection friendly encoding of the block reports. If you look into the patch, it takes over serialization of that block report data directly. It manually encodes the number of longs that are included in this block report, followed by a list of those primitive longs. So by doing that, we eliminate the array list reallocation costs, and we also eliminate the costs associated with boxing and unboxing. Another change in this area is Hdfs 9710. Which changed data nodes to send block receipt IBRs, this is incremental block reports, in batches. Incremental block reports had a tendency to trigger multiple RPC calls to the name node. When a data node receives a block, it sends that incremental block report information to the name node immediately. Even if it was multiple block receipts, this would still translate into multiple individual RPC calls, and so there would be a certain amount of overhead associated with this chatty call pattern. When you consider all the data nodes in a very large cluster, this could become a huge number of RPC messages and become a source of difficulty for processing at the name node side. The solution implemented in this patch was to batch multiple of these block receipt events into a single RPC message constituting a larger batch of incremental block reports. And by doing that, we've observed in testing that this scales better with respect to the number of nodes and the number of blocks in a cluster. Next, I'd like to shift to a slightly different topic that I call liveness. And this is a shameless lift from Wikipedia, so if you'll forgive me that. It defines liveness as a property of a system to make progress despite the fact that it has concurrently executing components and they all have to take turns on some kind of critical section. And in particular, this was coming up around the topic of data node heartbeat processing. Data node heartbeats are a means of reporting health of data nodes back to the name node so that the name node has a complete state of knowledge of the cluster and which nodes are healthy. We were observing that there could be operational problems associated with the load of those heartbeats and processing them in a timely fashion. This turned out to be a surprisingly costly operation because of the fact that we've kind of overloaded heartbeat processing to serve another secondary function, and that is for dispatching of work asynchronously back to data nodes. While we're heartbeating anyway, we take advantage of the RPC reply to say, here are some tasks that you need to do. And those tasks can be things like block deletions for blocks associated to files that have been deleted now. And calculating the set of work that needs to be dispatched is something that requires interrogating some internal data structures, and that all required contention on a global lock. Now, unfortunately, blocked heartbeat processing can have a tendency to become a cascading failure and become something much bigger than just an individual data node problem. The reason for that is because blocked heartbeat processing in the extreme really looks no different to the name node than a data node that has died, that is no longer running at all. When data nodes are not running, the name node will flag them initially as stale, put them into a special stale state, and then eventually mark them as dead and not really usable for anything in the cluster at that point. When there are multiple stale data nodes, a data node in stale state, some clients will seek to avoid using those nodes. And then once a data node transitions to dead state, the name node will simply stop dispatching clients to that. In addition to contributing to reduced cluster capacity, this can have a side effect of triggering a storm of wasteful re-replication activity, because the name node will see that this node has gone down and think that its blocks need to be replicated elsewhere to restore the replication factor associated with the files. We looked at this problem and came up with Hdfs 9239, which defines the data node lifeline protocol. And this is an alternative protocol for reporting the health of data nodes to the name node. It gives you the ability to optionally turn on a separate RPC server running within the same name node process. And that RPC server port is dedicated strictly to the handling of these lifeline messages. The lifeline messages can be thought of as a simplified form of the heartbeat messages. They report the health of the data node to the name node, but they're simplified in the sense that they do not take responsibility for that asynchronous dispatch of work back to data nodes. And that was really the source of the lock contention that we were seeing and the source of what was causing some bottlenecks around heartbeat processing. With this in place, even if the name node's main RPC queue is completely overwhelmed, the lifeline messages are still capable of keeping the data nodes alive. This is something that we were able to validate in testing. We were able to simulate conditions of an overloaded name node main RPC queue and observe that the data nodes were still able to keep alive and keep serving traffic. Expanding on that idea, Hdfs 9311 added a capability to offload a different kind of RPC call pattern to that same dedicated separate RPC server. And this is very critical in name node HA health check and failover messages. These messages originate from the Zookeeper failover controller in an HA deployment, and they're very important because they are used to determine if a name node is alive, and if it's not alive, telling it to gracefully fail over and initiating the entire HA failover process. We had seen cases of those messages getting blocked due to high load, but with the work done here, the enhancements done around the lifeline, separate lifeline server, those messages can be offloaded and they can keep processing. At this point, we've looked at a couple of different aspects of performance on the HDFS side. I'd now like to turn it around and look at it bottom up, I guess you would say top down, the opposite, I'll say, and look at the applications themselves. If applications are generating load on HDFS, is that load legitimate? In many cases, yes, because we see data sets continually growing and new processing continually coming online. But in some cases, the call patterns are suspicious, and it turns out it's because of inefficiencies in the way applications are written. And I don't say this to point fingers at applications so much. I have to admit, too, this is to some degree a fault of the definition of the file system API that wraps over the HDFS calls. That API, unfortunately, has some aspects to it that can make it easy to write code that is very easily read, but under the covers translates to an inefficient RPC call pattern. And the first example I have of that is Hive 10223. I have a very simplified before and after version of the code here. And it's very simple code. If you look at this, FS here refers to an instance of that file system interface. We have some logic that's saying if fs.isFile, do one thing, else if fs.isDirectory, do some other thing. It's very readable. What is unclear from just looking at this code in isolation is that it actually generates two RPC calls, and they're redundant RPC calls, as it turns out. isFile and isDirectory are really just wrappers over a more primitive RPC call, getFileStatus. And these helper methods are just interrogating separate properties attached to the response. So this is something that's very easy to consolidate into a single RPC call, as shown in the second sample. There we directly call the getFileStatus primitive, and then once we have a result locally in memory, we can just check isFile or isDirectory attributes on that response, and we've gone down from two RPC calls to one with a very simple patch. This kind of change is good for Hive because it reduces the latency of their operations associated with name node RPCs, And it's also good for the entire ecosystem because it's something that's subtracting load from a shared service. This code change might not look like much in isolation, but when you think about it in the context of a large cluster running many, many workloads, many, many Hive queries, little changes like this can add up to a more stable system. Similarly, there was PIG 4442, and this one is very much the same kind of thing, but it's actually even more obvious when you look at it because there are obviously two individual calls to the same get file status API here, and then you can see they're just getting different attributes out of that. So once again, it was trivially consolidated down to a single RPC call. This was something that we noticed through inspection of the Hdfs Audit Log. If you haven't seen this, it's something that was designed really with security auditing in mind, but it writes a record of each operation that the name node performs, by who, whether the operation was authorized or not. And we continue to find that looking at the audit log is a very, very rich source of information for troubleshooting HDFS and optimizing HDFS. If you haven't already, I recommend just an occasional spot check of the audit log. You may find that one of your own applications has some kind of inefficient call pattern. In this particular case, manual inspection of the HDFS audit log while submitting some PIG jobs revealed in rapid succession two get file status calls on the same path, which looked suspicious. And at this point, I'd like to hand it over to Arpit to talk about managing name node load.
Thank you, Chris. So now I'd like to spend some time talking about how we can help the name node be more resilient to these poorly written applications or poorly configured clusters. And, with name node HA, the name node is no longer a single point of failure in the system, but unfortunately, the performance of a single name node can still be a bottleneck to the performance of your entire cluster. And the reason for that is historically HDFS has assumed that applications will be well behaved. So that has two parts. First of all, applications will not be intentionally malicious, and secondly, applications will be well designed. And in a multi-tenant system, that's not a safe assumption to make anymore. And because of this assumption, it turns out it's very easy for a single badly written or badly configured job to completely overwhelm the name node and affect the performance of the entire cluster. So before I go more into specific improvements, I just want to give a very simplistic overview of the Hadoop RPC architecture. So the way Hadoop RPC works is that there is a single thread which picks up incoming requests from a socket and puts them into a shared. And then you have multiple handler threads dequeue requests from this queue and process them. Now what happens is that if the incoming rate of requests is higher than what can be processed by the server, this queue starts building up. You start getting more and more requests in the queue. And when that happens, the request latency starts going up. Eventually, at some point, the RPC request queue, can you guys hear me? Yes. Okay. At some point, the RPC request is full, and so that single thread that's actually dequeuing requests from the socket, that completely blocks. And now you have a backlog building in the OS socket buffers. And the problem with this huge queuing is that the clients are starting to see more and more latency. And when you have more latency, you have the chance of timeouts. And timeouts often result in job failures. So you have a positive feedback loop in the system where when the name node is overloaded, that's exactly the time when jobs start failing and they start doing more and more work because failed jobs are restarted. And so the system gets into a more and more degraded situation. And this kind of situation is usually impossible to recover from without some manual intervention from an administrator. Maybe an administrator has to go and kill some jobs. So how can we help the node be more resilient? So the first feature that I'm going to talk about is Hadoop RPC congestion control. And this was contributed by the community. And it builds upon a very simple idea that when the name node RPC queue is full, instead of blocking, the Hadoop RPC server sends a congestion control signal back to the client, kind of like how you have congestion control signals in networking. And what this signal tells the client to do is to back off and retry the request after an exponentially increasing delay. So every time a client gets a congestion control signal, it retries the request, but it doubles the delay sleep that it adds. And the good part about this is, first of all, clients know that the name node is still working, it's not gone. They don't completely give up and time out, so you reduce job failures. And the second nice effect is that as more and more clients get throttled, the overall load on the system reduces and the name node gets a chance to recover from this overloaded situation. Another feature that was added by the community is called fair call queue. So remember how the name node has a single shared RPC, and fair call queue now replaces the single queue with multiple priority queues. So the name node can now maintain a sliding window of history of RPC requests grouped by user. When a new request comes in, the name node looks up what was the activity done by that user in the last few minutes, and if it was a very heavy user, then that user is slotted into a lower priority queue. That request goes to a lower priority queue. Now you have these multiple handler threads, and they dequeue requests at a higher probability from the high priority queues. So you don't completely starve your high usage jobs, but you also don't let them affect the overall state of your system too much. And this feature actually works very well with RPC congestion control, because you can have congestion control messages being generated from your lower priority queues while requests are processed as normal from the high priority queues. So now we'll talk about Hadoop 12916. This one added a small improvement to RPC congestion control. There is one problem with RPC congestion control, and the problem is that it waits too long to signal congestion. It waits until the RPC queue is full. And if you wait, that already a good possibility that clients are seeing timeouts. So instead of that, this improvement lets you pluggable back-off policies. And one good example of a pluggable back-off policy is the name node can track its own RPC latency and start signaling back-off if the latency goes above some preset threshold. So now you're not waiting that long to signal back-off, and so you're further reducing the chances of timeouts in the system. Another improvement related to fair call queue is, so let me talk about one potential problem with fair call queue. It has a priority inversion problem. And the problem is that the name node is not aware of the relative priorities of yarn jobs. Sometimes you do want your high priority jobs, even though they are they are generating a heavy load, you want them to be processed with a higher priority. You don't want them to be deprioritized. That's because there might be some critical job that's very important. So how do you solve this problem without adding a tight coupling between the name node and yarn? So the proposal from the community is to introduce something called a resource coupon. And a resource coupon is something that a privileged user, for example, a yarn resource manager, can request from the name node. And this resource coupon guarantees a specific slice of the name node's processing capacity. Now this resource coupon is provided like a token to each job, and the job uses the resource coupon along with each RPC request. So the name node looks at that resource coupon and uses that as an input to decide which priority queue to slot that request in. Okay, so that was all for the RPC resiliency improvements, and I'm going to talk a little bit about logging. And logging is something that has a really outsized impact on the performance of a cluster. It looks very simple, but in fact, a large proportion of the cases that we have seen from users, the problems that users run into the field are related to logging. And the problem is that logging requires a very careful balance. You definitely want to log enough so that you can solve problems, you can root cause problems as they come up. But if you log too much, then that makes it hard for administrators to separate signal from noise. And secondly, logging is also very expensive. This was actually a surprise to me, but rendering strings is a really expensive operation. And not only is rendering string expensive, but writing them to file is a very expensive. So here is an example of a couple of log messages that were being logged by various Hdfs services. And these log messages consume a lot of CPU cycles, but they do not actually present any useful information. So the first message there is operation category read not supported in state standby. And this message is seen when a client connects to a standby name node. And the standby name node throws a standby exception and says, go away, I am standby, try the other name node. And this is a perfectly normal discovery mechanism by which clients learn which name node is active. But unfortunately, it results in this spam of log messages. And we had a lot of cases where administrators would see this message and get confused and file a case saying, what's wrong with my cluster? Why am I seeing this message? So the fix was to eliminate this message. Another example is a message that's seen on the data node. And this message is seen when a client connects to the data node and then disconnects immediately without sending any data. The data node message saying, I don't know what happened. But unfortunately, this is a very common programming pattern by monitoring applications. They want to know whether a data node IPC port is up or not. There's network connectivity to that port based for their various consoles. And so they would make a connection and immediately disconnect if the connection succeeded. And that particular act would trigger this spew of error messages in the data node logs and confuse administrators. And we also had a bunch of support cases related to this. So in both cases, the fix was to just get rid of the log message. Let's take some common logging pitfalls. One of the first logging pitfalls is that forgetting to use guards around debug and trace log statements. And this is really a property of the Apache Commons logging API. The problem with this API is that it statements. I'm sorry, I don't know what's going on with the mic. Okay. Okay, so the Apache Commons logging API has this property that it always pays the cost to render the string, even if the target logging level is suppressed. So for example, debug and trace log statements are off by default, but you're still paying the cost to render these expensive strings. And so a simple fix is to add logging guards around the log statements, but it may come as a surprise, but programmers sometimes make mistakes, and they forget to add these logging guards. And so the better fix is to use an API like SLF4J, which is a very thin wrapper over other logging frameworks. And SLF4J in most cases can eliminate the need for logging guards. Two more problems with logging are first logging in a tight loop, and secondly logging with a very expensive lock held. So the worst example of this is the name system write lock. And if you are at all familiar with the name node architecture, this is a big global lock that must pretty much be taken to process any user request or any block report from a data node, of which thousands of events occur every second. And so if this log is held and you're writing out a lot of logs, you have the potential to completely stall the name node activity. And we saw this occur in practice with this bug, Hdfs 9434, where when we would recommission a data node after some time of inactivity, the data node would wind up reporting all these blocks, and the name node would wind up writing one log statement for each block. And in the worst case, with 500,000 blocks, you would see that the name node completely stalls for 30 seconds. And actually 500,000 is not that uncommon. We are now seeing fairly common for data nodes to have up to 5 million blocks each. So the simple fix was to change this from an info to a trace level, and also use SLF4J, so we are not paying the cost of rendering this string all the time. And the last topic I want to touch on is troubleshooting. So for troubleshooting, if you have used any cluster management tools like Ambari, they show a lot of nice graphs and visualization. And all of those are driven by metrics that are generated by these various services. So metrics are really important. And you want to see two good properties from your metric. Metrics should be able to tell you that there is a problem with your cluster. And ideally, metrics should also tell you what is the source of the problem. So one recent improvement, again, this was contributed by someone in the community, is a feature called NNTop. And Chris talked a bit about the Hdfs Audit Log. There's an example of what an audit log entry looks like. So this audit log entry tells you that a user named Bob sent a list status, which is basically get file information on a particular directory. I'm sorry, a list status on a particular directory. Now the problem is that the Hdfs Audit Log has a lot of details, but it's very difficult to get quick instant insights from. It requires some ad hoc scripting, and pretty much every administrator has some awk Perl scripts in their in their back pocket, which they run on these audit logs to get aggregate information. So the feature that was added by the community is called NNTop, and it introduces a new metric called top user op counts. And for the 3 windows of 1, 5, and 25 minutes, it tells you what were the most frequent operations on your name node and what were the operation counts grouped by user. So here's an example of running this metric from a test cluster, not a real cluster. We don't have real users named Alice and Bob. Okay, so here's an example from a test cluster where you see that user Alice has created over 4,500 files in the last 1 minute. And lastly, I also want to talk briefly about Kerberos. And Kerberos is the one thing that really strikes fear into the heart of every Hadoop developer. If you get a if you get a Kerberos-related ticket, then forget the rest of your day, the rest of your week is gone. So, and that's because Kerberos has a lot of moving parts. It depends on your Kerberos KDC being set up correctly. It depends on your DNS and reverse DNS being set up correctly. Also, you have a bunch of principals and key tabs to generate for each of your services. And finally, there must be multiple configuration settings for each service that must be set up exactly right. And management tools like Apache Ambari automate a lot of this initial setup, but they don't really help you diagnose problems when something goes wrong. And also another problem is that with Kerberos, the error that you see is very far removed often from the root cause of the problem. So it might take a long time to work back and figure out what went wrong. So another improvement that was made by the community is called Diag, and it's a very simple command line tool that any administrator can run. You can give it a service principal and a key tab name as input, and it'll go ahead and run a bunch of diagnostic checks around Kerberos and sort of sanity checks, and we have more checks in the pipeline that are being added by the community. So here's a very simplistic example of running Diag in a cluster that is where nodes cannot actually look up their own canonical host name correctly. And believe it or not, this does happen in real clusters. So that's the error message that's printed out there by Diag. So in summary, we have looked at the following classes of performance improvements that we have made: performance, stabilization, supportability improvements that we have made to HDFS. And at this point, we'd like to open it up for Q&A. And while we answer your questions, there's a slide up there that has a list of things that any HDFS cluster administrator can do to help make it easier to manage and diagnose problems with your cluster.
So is there any consideration to help the primary name node by leveraging the standby name node and read requests? I mean, the standby to a certain degree knows what's going on, and you can help with the RPC issues. Is that?
That's a really good question. We don't let it do that because it's not uncommon for the standby to fall behind the active in processing transactions. So the way it works is that the active name node is continuously writing transactions to its edit log, and the standby tails these transactions and rebuilds its state in memory. And so there can be a delta. And it's not rare for this delta to be hundreds of thousands of transactions. So it would be a nice improvement to make, but we don't have that yet. Sorry, the question was that is there any plan to leverage the standby name node to help serve with the read request load? Because the standby name node also has a complete state of the file system in memory.
Have you seen bigger name node heaps when the young generation takes longer? And have you changed the garbage collector to address that issue?
Yeah, I'll repeat the question. Let me know if I got it right. You were asking if you've seen with larger name node heap sizes, if there is a problem in the young generation, and if you've needed to tune garbage collection in reaction to that at all. Does that sound accurate? And the answer to that is yes. We have a set of recommendations around name node heap sizing and also garbage collection tuning to go along with that. And specifically, there's a formula we use. Once you have your target heap size for the name node, the new generation, we choose 1/8 of that total size for that, but a hard cap at, I believe, 8 gigabytes, so never bigger than 8 gigabytes. We also have some recommended best practices around using concurrent mark sweep for the name node's garbage collector, and there are some other tunings that go along with that too, such as the CMS initiating occupancy fraction, which is a hint to CMS to kick off its full garbage collection cycle ahead of more rapidly than what it would normally choose according to its own internal heuristics. And there's a talk happening, not the next talk in this same room, but the talk after that I'm back up here with a coworker with some more operational war stories and things that can be done to address it. And garbage collection is a specific topic in there.
Have you seen cases of data loss with Hdfs? And if so, can you share your experiences of what could be causing it and how common it is?
Bugs. So we had an unfortunate, and I'll actually stand up and take the blame for this. A code change that I made introduced a race condition that led to a data loss scenario. And it was a fairly rare data loss, but we had a few unfortunate cases where it did result in real data loss. So yeah, bugs would be one case.
I think too sometimes there can be cases where it's simply too easy to delete stuff. And there are some protections that have been put in place around that. You had a recent enhancement
Yeah,
in
so
there, right?
we have so you know that if you delete files on the command line, the name node actually moves them to trash, and there's a skip trash option, and that's really the equivalent of rm minus fr, and it's unfortunately common for administrators to do rm minus skip trash on /users, and that's like the equivalent of doing rm minus fr /users, and then we get a panicked call. So we have a feature in Hdfs called protected directories, where you can mark certain directories as protected, and even a privileged administrator cannot delete those directories without some really complicated sequence of steps. I'm sure that if you make it more difficult, someone will figure a way around it, but it does add an additional step.
In what version of HTTP we expect all the RPC call improvements will be available?
They have been shipping in HTTP and Apache Hadoop for a while. So they were part of Apache Hadoop 2.6 and also HTTP 2.3. We are currently on HTTP 2.4.
And the resource coupon part of it, that part's still under active development. But yeah, aside from that, it's all shipped.
Any thought about federated name nodes to help with the scaling?
So federation is actually a great feature, but it's difficult to use because federation breaks rename across arbitrary directory boundaries. And it turns out that there are a lot of applications which rely on that. Applications rely on being able to put data in, generate data in one location, and then atomically move it to another directory. And federation breaks that. So federation is hard to deploy. There are some customers who have deployed federation successfully, and I believe there are some large companies out there who are using federation successfully. But in general, federation has some problems with regards to application compatibility.
Let's say that I have a name node with a very high RPC workload, but my data access pattern is okay. There's a way that I can upscale the hardware or something that may help the name node to process faster the RPC, or
as far as growing RPC capacity at the name node, that would likely be looking at a vertical scalability solution at that point. There are some more forward-looking directions in HDFS around, the talk has already passed at this point. It was earlier on the schedule, but there was growing HDFS into a generalized object storage platform, and that effort is looking more into distribution of load more so than current HDFS does for various operations. So things that were traditionally metadata centralized at the name node, we're looking at ways of pushing that down to lower layers, a kind of data node equivalent layer, a container layer that would be able to field more of those metadata operations. You might want to, if you hadn't seen that talk earlier, that might be one to go back and look at when the videos come out.
Also, that talk was also given at Hadoop Summit in Ireland earlier this year in Dublin, and it's on YouTube. So yeah, you can go and watch that talk on YouTube. It's called HDFS Futures.
I have seen in many cases, like block manager spams the name node login. So is there any improvement in user readiness
Yes, there have been a bunch of fixes kind of playing whack-a-mole with the log statements that generate spam. So we have dialed down a lot of logging, and it's gotten progressively better over multiple releases. I think if you look at Apache Hadoop 2.7.2.7.2, which is the latest stable release out there, or HDP 2.4, you will see that it's much better.
So I have a question regarding the data node lifeline protocol. So wouldn't that cause more write failures because, so clients can still write to that data node, but data node is then not able to send any block reports to name node. So name node wouldn't allow to close that file because it's not replicated.
So that is a concern, and that is something that came up in design reviews around that. In extreme cases, that kind of thing could happen. We still saw the Lifeline protocol as something valuable for us to do, though, because it also had the benefit of saving a cluster from a lot of that wasteful re-replication activity. So even if, in the extreme case, that kind of thing were to happen, we still saw value coming out of the Lifeline protocol work.
We've just been told that time is up and we have to step off the stage, but we can take more questions off the stage.
Thank you, everyone.
Thank you.